fish using countercurrent exchange have more efficient uptake of oxygen than a mammal. Birds have better lungs than a mammal in the sense of being more efficient. The structure of a bird lung in schematic has air coming in. It has two air sacs that are not gas exchange. Not gas exchange, anterior and posterior, and then a gas exchange region in the middle. These parallel tubes called parabronchi. They are like your bronchi in shape, but they are unlike your bronchi in that these are gas exchange regions, a series of parallel tubes. How do bird lungs work? You need to start with the Mickey Mouse ears version of a bird that I draw all the time. Here are the Mickey Mouse ears. The parabronchi are a series of parallel tubes here. There's an anterior air sac, not used for gas exchange, and a posterior sac, not used for gas exchange. The gas exchange region is in this middle region here. In that region, blood is coming in the opposite direction in what can be considered a countercurrent exchange, in which the air is always going in this direction and the blood in an opposite direction. It's not quite a true countercurrent exchange, and it's sometimes called cross current for that reason. Okay, so how does this system work? It actually takes 2 cycles of inhalation and exhalation to move all of the air in and through this whole system, but we don't need to consider both of them in order to understand what happens. When the bird inhales, it's expanding the chest cavity. At this time, the way that air can exit from this anterior sac is closed. So this is inhalation. These sacs are expanding, and as they expand, that creates negative pressure. Air moves in and moves into the posterior air sac. At the same time, this anterior air sac is also expanding, and so air is being pulled in. What's happening is that air is filling this posterior air sac from the outside of the bird, but air from the air sac is also moving. So notice we have one-way flow of air, and remember the air is going in the opposite direction. That's inhalation. What happens with exhalation? We need my Mickey Mouse ears version of a bird. But now we're going to do exhalation. During exhalation, this opens. This is closed. And during exhalation, the chest cavity is compressing both air sacs. It's actually both sets of air sacs. There's more than one. Because it's compressing, air is moving out of the posterior. Remember, it can't get through this closed area. So air is moving in this direction through the parabronchi. Air is also moving out of the anterior air sac. So we get air moving down and out. So during exhalation, also we have one-way flow of air from posterior to anterior. So in inhalation, because the closure was here, as the bird was inhaling, it was pulling air into the posterior air sac, but the anterior air sac was also expanding, and so air was pulled from this part of the posterior air sac forward, one-way flow from anterior to posterior. And in exhalation, because this one is now closed and this one is open, in exhalation, pressure is pushing air out through here, but there's also pressure from the back on this posterior air sac, pushing air again one way. So with both exhalation and inhalation, air is moving through the parabronchi. Finally, notice that the air that is going through the parabronchi is never mixed with oxygen-depleted air. When the air comes in, it's at 160 millimeters mercury partial pressure of O2. That air is still 160 when it enters the parabronchi. When it leaves, depending on how depleted the oxygen has been in the blood going in the opposite direction, it might in theory be as low as 0 millimeters mercury partial pressure of O2. And we've never had any mixing. All that's happened is as it's gone through, it's been depleted to 120, 80, 60, 30, and eventually 0. Now, the parabronchi look like a bronchiole in that they're tubular, but extending out all along and all around are what are called air capillaries. As the air moves through, these tiny air capillaries are picking up net movement of oxygen going in and, of course, carbon dioxide going out. The blood is moving in the opposite direction, deoxygenated blood here. And as it moves, it picks up more and more oxygen. So again, this is a countercurrent exchange system. The oxygen content might be at 160 millimeters mercury here. And at this level, it's encountering blood that is fairly high in oxygen. So perhaps the blood here is something like 158. But that still means that there's a net movement of oxygen into the blood. We're going from 160 to 158. By the time we get a little further down, we're at 158 here, but now it's encountering blood that is 156. That blood is still coming from the deoxygenated blood coming from the anterior, and so again, you still have net movement. And all along, all the way to the end, where you may have something as low as 4 millimeters of mercury oxygen, here it may be encountering blood that's at 0 or 2 millimeters of mercury of oxygen, and so you still have oxygen moving. All the way along, you have just a small gradient between the air in the parabronchi and the blood that is passing, 80 to 78, and all the way along you have net movement of oxygen. The result is that the exhaled air may have near 0 when operating at its most efficient, whereas the blood has accumulated nearly all. It might have received 98% or more of oxygen from the air. That high efficiency means that birds can remove oxygen from air that mammals would find it impossible to do. That's the basis of the observation that on Mount Everest, climbers have been exhausted trying to get that last little bit up to the top of Mount Everest, watching Himalayan geese flying by overhead doing fine. Himalayan geese are capable of flying at elevations that humans can barely survive unassisted. In fact, without extensive training, cannot survive unassisted.